Great. Well, thank you for all being here right after, so punctually after the coffee break. So my name is Jitter. That's me over there. You may also have seen this guy running around the corridor. Jared is in the audience. He is the person who actually did most of the work, so I'm going to happily direct most of the questions to him. So today's talk is nominally about Julia, but it's really about the very difficult statistical problem that turns out to be benchmarking and performance testing. So a little bit about me. I actually did not study computer science. My background's in physics. And at some point, I said that I didn't want to be a physicist anymore, and I had the opportunity to start the Julia lab at MIT. So I did that for about 5 years. And then I decided that it was more interesting to do work than to apply for grants. And so I left, and now I work at a place that has a lot of money, which is Capital One. And I am now the lead of the Fair and Explainable Machine Learning Research Group at Capital One. If you're interested, please come talk to me. Or you can find this guy. This guy will be happy to take your suggestions as well. That's my contact information if you want to find me on social media, or you want to look at the previous talks I've given. If for whatever reason you're interested in all the Julia talks or all the physics talks I've given. Today turns out to be the Julia Day at Splash, which is kind of interesting. So if you were looking for one of these two talks about Julia subtyping or dynamism and performance, unfortunately you've already missed them. You can probably travel back in time to go see them, or maybe go look at the talks that were recorded. You're here. Jeff, who is speaking immediately after me, will also be giving a Julia talk. And if that's not enough Julia for you tonight, there is a user group meetup at CSAIL. If you're not sure how to get there and interested, please let me know. I'll be happy to point you the way and bring you there. So today's story is really about trying to justify how we ended up getting interested in the benchmarking problem, and what we've done in Julia to try to put into action some sort of rigorous framework to answer the question of how fast Julia is. So the disclosure, even though this is billed as a Julia talk, there's not very much Julia, but please ask me questions, especially since it's a smaller room. I'm happy to be interrupted and answer questions. There is math and statistics, so please don't be frightened if you see formulas. I apparently just killed my presentation. Excuse me. That was not part of the plan. Okay. So this is a story about 2014, and I was involved in 2 grant applications. And at some point, we went through an inflection point of Julia is too new and unproven to fund, reject, to Julia is already well established and doesn't need more funding, reject. So somewhere in between, we sort of missed the golden opportunity to apply for a grant. I'm still not sure what exactly happened here. But it's 2014. In 2014, I think the story about Julia being a general purpose language was really not as well established, even though it was designed to be general purpose from the beginning. We told people that it was a fast dynamic language for technical computing. And so dynamic language, I think, it's not difficult to see that it is a dynamic language. That it was designed for technical computing is also not difficult from the history. But really, it came down to this word, fast, which is maybe the easiest English word in this sentence. But what does it really mean in this context? And even more basic question is, if I have 2 programs, how do I know which one is the faster one? And I think for people who haven't thought about benchmarking before, this might seem like a really, really silly thing, an obvious thing to be asking. Like, obviously, you just time them both and see which one is faster, right? So why isn't it the same as asking whether this person, Rita Jeptu, who won the Boston Marathon in 2014, is she faster or slower than the Green Line train that she's running next to? Right? I love this GIF. I like to show this to everybody who has not lived in Boston before, to say this is what public transport in Boston looks like. Well, how bad can this get? So statistically, it turns out this is an extremely complicated problem, and there have been many papers, not just in the programming languages discipline, but also in supercomputing, in like computer systems and hardware, There's lots of papers and lots of little communities study this problem. So some of the bad behaviors you see here, this particular one was from a paper on benchmarking Xeon PHYs. You can see here that most of the timings for this one benchmark kind of cluster around here, which is great, but then there's this like small but very significant pile of very large outliers for this problem. This plot I think is really interesting. It's a phase plot showing the interaction between subsequent timings. So you're just basically plotting the 5th iteration versus the 6th iteration on this plot, and the 7th against the 8th, and so on and so forth. And you see that for this particular benchmark, that you actually have a really large correlation between subsequent measurements. And then here, this paper, which was presented at UPSA last year, you see very large changes in the baseline behavior of the measurement. So this last one, I'm just going to give a shout out to the work that was done last year in Vancouver. This paper came out around the same time we were thinking about our benchmarking work in a somewhat different context in terms of virtual machines. This is what we saw when we started playing with our own Julia benchmarks and went, oh great, this is going to be really interesting to try to describe as summary statistics. These are just 4 very simple benchmarks we've written in Julia, and these are real timings we've gotten for the 4 of them. So you can see all sorts of statistical non-idealities in this data. The fact that it's not IID, you've seen already. Long-term drift, for example, like these timings just keep steadily getting worse, and not really sure why. You know, bimodality, that there's multiple clumps, there's skew, there's large outliers, and the list just keeps going on and on. This brings us to us trying to actually address and solve these statistical challenges in an operational environment. So what's actually going on underneath? I think this is sort of the one-sentence summary here, that the execution environment is stateful on a modern machine. Like, we're long past the time where we can guarantee that the computer running your program is only running your program. It's doing something else behind the scenes. There's a whole bunch of names for this phenomenon. I think the most common one I saw was OS jitter, but it's really not just the OS. The other thing that was really interesting is how many things could be going on. We'll see that later. But first of all, here's a very simple Julia program. I feel like even if you don't read Julia, that it's pretty clear that you're doing some sort of summation, and you're accumulating a total, and you're just storing that total in X. And this is not a particularly difficult program, but the timings here, this is the one that gave the bimodal drift behavior. So you really have to wonder what's going on here. Is there some n dependence? Is there some size dependence? Is there, what exactly is going on here? This is one of the 4 we're here. I actually also did not, when I was starting this work, could not find a comprehensive list of all the things that could cause OS jitter. And so this is the list that I compiled at some point, and then decided that that's probably enough to make the point that there's a lot of things going on. So everything from like, error recovery and the ECC RAM to cache misses to like dynamic frequency scaling, just like context switching in general, job switching, everything to cosmic rays destroying your machine. This actually, there was not a paper about this, but I found an anecdote on the internet, so you know that that's a valid factor to put down. All right. So basically, most of these things, interestingly, I think we can summarize as causing delays and not speedups. So we'll come back to this. If we think about latency, it's not just the fact that there are many sources of latency, but the fact that they also happen with vastly different timescales. So this is something I pulled off a Berkeley website, but it's really based off of a somewhat well-known list by Peter Norvig back in 2001. It's been updated for 2018. This particular page is fun because you can go back and look at historical numbers and look at the comparisons of these things. So for those of you who are quite far in the back, I know this room is really hard to read, the words these small. So one of the black squares is 1 nanosecond. That is 100 nanoseconds. One of these green squares is, I think, 10 microseconds. And then one of these is 1 millisecond. So you see like multiple orders of magnitude being spanned, right? So this is 10 to the minus 9, 10 to the minus 6, 10 to the minus 3 over here. So all sorts of crazy things can be going on with literally orders of magnitude difference. And so, I don't know how many of you have seen this Grace Hopper video about what is a nanosecond. This is one of my favorite talks for early computer history. So this is a really, really bad screenshot resolution, but she's holding here a length of wire which is almost 12 inches long, and that is how long it takes for the electrical signal to pass through that much wire in 1 nanosecond. And then here she has a microsecond, which is like this giant coil here. And she says that not even Hercules could lift the millisecond wire. So I really like this, this particular demonstration because it really puts into context what this means when you're looking at latency in your program. And of course, this poses a huge challenge that is very hard to nail down statistically. So going back to what you would probably do at first blush, which is me about a few years ago, was like, well, isn't it obvious you do some statistics, right? You just keep repeating your timings and then you report some sort of mean and standard error, maybe do a means difference test or a ratio test to actually determine if the programs are faster or slower. Maybe I want to warm up the machine, so I'll run up some warm-up runs before I take the timings. And then also I want to time a whole bunch of them together so that you can get the resolution down for very, very short programs. The problem is, when you see a timing statistics like this, when you actually collect them, this particular program invalidates all of these techniques. First of all, there's no obvious warm-up period in these timing data. The mean is a really bad way of summarizing this data. It doesn't capture the fact that it's bimodal and has systematic drift. And improving timing resolution doesn't really help with the fact that if you just look at a chunk like this, you get a bunch of the fast and slow timings all together. So no matter how you chop this up, you're going to end up with a mean that's somewhere in the middle here that is not actually reflective of an actual run of this program. So I went back and said, okay, well, surely this is a solved problem. Famous last words. So this is all the things that I've seen people have tried to do. Let me try to summarize these. So I think of them as better statistics, better reproducibility, and better timing resolution. So for better statistics, people have pointed out, hey, real data is highly non-Gaussian, but then I think they have not actually taken it to its logical conclusion where they say, well, it's non-Gaussian, which means that if we just correct for the fact that it has a skew, then we're fine. But really, these kinds of methods are only good for weakly non-Gaussian. So if it's like still somewhat Gaussian, but just like a little bit lumpy on one side, like you can correct it that way. But what we've seen earlier is that we do have highly varying magnitudes of the size of outliers you could get, at least on paper. So moment correction methods we don't think are particularly good. Using the mean or robust statistic doesn't help with the fact that if you have bimodality, you're still going to have a problem in describing the fact that there's two clumps of timings. Removing outliers with, for example, the 3 sigma rule, this is actually, there's a hidden Gaussian assumption there that says that, inherent in the 3 sigma rule is the fact that 3 sigmas away from a Gaussian is very unlikely. So if you're not careful about that, you might actually run into the risk of just deleting all the important outliers in your data if you just run this as a blind test. So improving reproducibility, there's actually quite a lot of interesting work in this area, which we fortunately were not able to use because these were either OS specific or like build specific or even compiler specific techniques. But it's quite interesting to see what people have tried. So one of the things that people have pointed out are things like the fact that a compiler or linker may arbitrarily decide to lay out symbols and binary blobs in different parts of memory. Like there's no reason to say that if I've actually two binary compiled library functions, that the first one needs to precede the second one, for example, or that they're even contiguous in memory. So one attempts to deal with that problem is actually guarantee that at the compiler and linker level that you have a reproducible binary layout. And if you carry that idea further, there's also the completely opposite thing you could try, which is to always completely randomize the layout, which in itself is a interesting take on the reproducibility problem. There's also things like making the garbage collector less variable. There's also running a custom OS kernel that is designed for low jitter, perhaps with like a low swappy VM or something like that. The one issue here with these particular techniques is, are these timings really realistic of the actual execution environment of your program? So it's a bit of a metaphysical question. Like, yes, you can get better numbers, but are they really reflective of what's going on underneath? And we'll come back to that question in a little bit. And finally, we have improving the timing resolution. It's an interesting question of how to actually do this correctly, and we'll see our proposed solution to this in a couple of slides. As we've talked about, most summary statistic methods still preserve the nastiness or amplify the nastiness in the program. So what we're seeing here is taking this data and actually just running it many times and then collecting summary statistics. And so doing groupings of the raw data. And so you see that the mean essentially reproduces the same drift and bimodality that was inherent in the original data. The more robust statistics like the median and the trimmed mean, interestingly, occasionally pick out the fact that it is bimodal. But again, if you're going to take something like the average of the median or something like that, it's still not going to be a good summary of what happened. And finally, just plotting here the minimum time. So we're going to argue that there is one context in which the minimum time is actually the best statistic you can use, which is sort of a very strange thing to say if you think about it, but we'll come back to that, and I hope that people will give me a hard time about it, because I think this is a somewhat unintuitive thing to claim. All right, so our approach here is we're going to focus on getting better statistics. We're just going to account for the non-ideal statistics from the very beginning, rather than trying to correct it afterward. So this let us think about a very simple model for how you might describe fluctuations in program timings. So consider a noisy syst machine for simplicity. We can talk about the generalizations later. And if we think of the program as just a sequence of instructions going from 1 to k, and furthermore, this machine isn't guaranteed to just run your program. It could at any point arbitrarily decide to run some of these extra terms which may represent something like swapping to disk or like a cache invalidation or something like that. So we're just abstracting all of that away as just additional yellow boxes that can be interspersed with your program. And the machine's actual operating system, as it were, is really just this algorithm. So you say, I run this instruction, and then I choose at random for each of these factors whether or not it executes. And this gives me an actual sequence of instructions that's run that looks like this. So it's the light blue boxes, but they're interspersed with an arbitrary number of the yellow boxes. Okay, so this is our proposal for how we can think about delay instructions as just random insertions into the instruction tape. There's nothing here about IID, there's nothing here about Gaussianity, but it does assume that the delay factors are pure, they are independent, and furthermore that they're pure delays, so none of these like magically make the program run faster. You could, in theory, introduce something with a negative characteristic time, but it's not. We don't think it's going to happen very much in practice. So, suppose I want to know the running time of this program, the program I thought I typed into the computer, right? But we know that the machine will insert these delays, so we're actually going to get multiple different timings over multiple different runs. So what happens when I just average over the timings? It's not very hard to show that you essentially collect a whole bunch of these delay factors, and there's a random variable you can write down that is just how many times that factor was triggered as part of the execution. And if you take the average, so I'm using angle brackets here for averages because I'm a physicist and I really don't like statistical notation. This machine-specific term, this term, like how many times the delays were activated, that doesn't go away. And you can see by definition, this is a positive number, this is a non-negative number, so this term is at best 0, and it's going to be strictly positive, right? So there's no expectation here that this will be Gaussian in any form. We'll talk about timer resolution later, it doesn't quite go away. So perhaps the obvious conclusion is, well, if you just run it once, it's not going to give you a good estimate of the running time. You already knew that. So can't we just run it a lot of times and then you can go for an extra coffee break? What happens when you actually just copy the program n times? You just splice n copies of this tape together and run it through the program. So if I make n copies of this, I might be able to estimate the time needed to run any one of these just by timing this total longer program and just dividing by the number of repetitions I made. Well, you have to insert all the delay instructions, and the main result, again, is perhaps not surprisingly by construction. The best case is that the delay factors trigger small O of n times, in which case you can ignore that term, that was the machine-specific delay term. And in the worst case, every delay factor triggers all the time. So you just add all of them up. And what this really says is that the empirical timing doesn't always converge to the program execution time for just one copy of this. In this model, at least, it is always upper bound at best. So for this problem, we're saying that if we believe that most causes of jitter are pure delays and not speedups, that the thing you should be using is the minimum. And we've already seen that in practice, it's not completely crazy to think that this is plausible because it washes away all the non-idealities. So why haven't we solved this problem? And Jared likes to give me a bit of grief about this because I think in some version of this paper, we sort of claim we solved the problem, and yeah, we haven't solved the problem. So I gotta put this out there. It's not a complete resolution to this problem. This statistic itself has some very weird behaviors. So putting error bars on the minimum is actually a very difficult problem. And if you think about it for a little bit, it's not surprising because it's pathologically sensitive to the smallest data point, right? And then maybe somewhat sensitive to the second smallest data point. That's maybe the error bar that you would get. So it's actually really hard to put an error bar on just the minimum. And then the more philosophical problem here is this program, the program that we put in here, that is just this, is that really the timing you want? So, and I don't know if we have an answer to this question other than to say, hey, that's a different timing, right? So the platonic ideal time of that program with no delays is perhaps theoretically attainable, but maybe in practice never attainable. And maybe how long you want to compare it to is intimately tied to its interaction with the environment. Because you may never be able to run this program without incurring a disk swap or something like that. And then what are you going to do? It does help in this one problem, which is this problem of amortizing the timer resolution error. So if we go back to this problem again, where we have this program to run, and we have a finite time budget to run this benchmark. For example, if I'm on the free tier of Travis, it will time out eventually, so I don't want to run it for too long. And I also know that the timer has finite precision accuracy. So on some systems, you get very high resolution timers, in which case you don't really need this, but on some other operating systems that will remain nameless, it's notoriously difficult to get good high resolution timers, and even timers that claim to have high precision are not necessarily that accurate. Right? So as a classic measurement problem, these are actually two different sources of non-ideal behavior for the timer. So now the question is, how many times should I repeat this program in order to get the best possible estimate within the time budget that I've set out? So this is the algorithm that we have in our paper. It's really not that difficult to see that what we're proposing is just run it once, twice, up to j times, and then you just divide by the number of times you run, and you take the minimum time, which we just argued that is probably the best thing you should be doing in this case. And then you evaluate this oracle function, which tells you, based on the timing that you got for the program, how many of these repetitions you should be doing. The oracle function, we're going to cheat and say this is actually sort of a self-learned function. It really just gives you that mapping from runtime of the function to the proposed number of measurements that you have. And so this is something we don't know. We can just do a Bayesian update, as I've decided to call it today. And if you look at what happens in practice, you can actually see that, yes, there are all these crazy timings that go way off the chart here. We just truncated this to 150, but the original timing is here, way up here. But you can see that there's a very nice envelope of the 1/n convergence that you see for this particular problem. So we think that for at least this one problem of amortizing the resolution, it's okay. And then I'm going to talk a little bit about the production infrastructure for benchmarking in Julia, because I think it's kind of a fun problem to see how we got involved in this. So this is what the Julia CI org on GitHub looks like. It's a fun, it's an interesting repo to look at because most of the activity on this is done by non-humans. There are three of these key algorithms, or rather software packages. There's BenchmarkTools, which Jared wrote, which implements the linear scan algorithm that we saw. It provides this macro in Julia called the B-time macro, and so this gives you that algorithm which we've just described, which tries to give you a very accurate estimate of the runtime of very short functions. There's base benchmarks, which is a curated collection of benchmarks for Julia and its standard library. I've asked for a number of how many benchmarks there are in here. There are almost 3,900 benchmarks that we run, I think, in full on an almost daily basis, assuming our machine doesn't crash. And then people can call in an ad hoc fashion for more tests. And NanoSoldier is our GitHub bot for actually connecting user queries for running the benchmarks on our machine at MIT. So this is what happens slightly behind the scenes. Jared is laughing because I have this picture of the NanoSoldier bot. So what someone does here is someone who has commit access to the repo will say, at NanoSoldier, run this command, run all the benchmarks, and then NanoSoldier will dispatch this and run it on our machine that's hosted at MIT. The performance report gets committed to a base benchmark reports, and then you get a little comment that says, your benchmark job is completed, there might be performance regressions, there's a report, there's a link you can click, and it goes to that repo, and you get something that looks like this as part of the report that says, we think that maybe there's an issue here, there's an improvement here, there's like a regression here. This is both timing regressions and also memory usage regressions are reported here. I think overall it works quite well. Most people seem to think that it's a useful service. So we're not burning CPU cycles endlessly for no discernible value. But there are some challenges that we encountered in production, which I thought would be good to highlight. For example, what is a performance regression is actually not a question we really answered yet. We've just said for now that it's a 5% increase in runtime or a 5% increase in memory use.
It's actually a variable based on the benchmark.
Okay.
Yeah, so 5% and 1% for memory use are the defaults, but then some of them have increased, like up to 25% for some particularly noisy benchmarks.
Yeah, so just to repeat for the recording that it's 5% in runtime is the default for running time, and it's 1% for memory use, but these can be adjusted on a per benchmark basis, and we apparently have done that quite a bit. Yeah. There is a problem here, which if you heard a talk on Monday that was not recorded, you may have seen vestiges of this. We think that there's a problem with what we have in terms of alarm fatigue. So alarm fatigue was this phenomenon that was really described for nurses and doctors, where if somebody keeps flatlining or there's an error that keeps going off and the alarm keeps going off in your head, you very quickly learn to just ignore it. And in this case, nominal performance regressions, I think, are prone to this particular psychological use issue, where I went back to go look through our GitHub findings. I've noticed that, first of all, this is not quite a complete number because GitHub searches can only search on comments on issues and not comments on commit hashes. There seems to be an issue with the GitHub search. So these numbers are not quite complete, but of the 522 performance reports that I could find from NanoSoldier, 503 of them have reported performance regressions. And I think 1 or 2 of them were just user errors, like the user ran something and you didn't say what to run, so it just didn't do anything. So only about 16 of these actually ran fine and there were no regressions. So this is a really, really high number. I think there's some digging to do as to what were the real regressions. We could probably randomly sample some of these to see if the developer discussion afterward said that this was a real regression or not. But nonetheless, we think that 96% of the time is probably a little bit too high to say that every time you made some change to Julia, you made a severe regression of this size. So this is probably something worth investigating as a future topic. And the last thing is maybe a little bit specific to Julia, but probably not super specific. We just have a very large benchmark suite. It takes a really long time to run. And so you have the problem where people just ignore it because it takes too long to run. There's a combinatorial explosion of combinations we could test simply because of polymorphism. And Julia was designed for polymorphism from the beginning as one of the selling points. Again, not unique to Julia, but I think every time you have this possible exponential growth of possible combinations to test, you quickly run into the question of, should you test all of them? Or do you just want to test a few of them? If you want to test a few of them, what do you actually want? In practice, people tend to run just the subset that they think they're interacting with. But of course, this runs into the risk of saying that maybe I have some coupling with some other part of the standard library that I didn't think about at first, and I'm just going to look at the part that I thought I'm touching. I might miss some interactions that might lead to regressions down the pipeline. So in summary, things we probably got right so far is what we think is a justifiable Bayesian approach to benchmarking really short programs on noisy machines, taking into account non-Gaussian statistics from the very beginning, and the fact that the machine itself is going to give you an arbitrary amount of OS jitter. And secondly, I think there is empirical success in adopting a culture of regression testing as part of Julia-based development. And this was definitely something that was done on a much more ad hoc basis before NanoSoldier became online. And so we like to think that to the extent that we're doing this correctly, that we're still holding true to the original promise that Julia was a fast language for technical computing. There's loads and loads and loads of unfinished business and also opportunities for people to work on projects with. I'm not sure if at Capital One will be able to help with this, but certainly there's lots and lots of interesting questions here to contribute to Julia, or even just the general problem of benchmarking, and maybe get some papers out of the work here. So just to summarize, there's rigorously defining what performance regressions mean, alarm fatigue, speeding up benchmarking for very, very large exponential combinations. There's maybe trying to make more rigorous the notion of confidence intervals or error bars on the minimum time estimator. And then there's the generalization to SIMD and LIMD, which I think is an interesting open area. There's been some papers on benchmarking parallel systems that have made claims that these are intrinsically more difficult problems. So it'd be interesting to see if this was actually something we can nail down more precisely. And that's really it. By the way, I'm hiring, so that's my talk. It's a little bit shorter than usual, but thank you very much. Yes, Jared.
Yeah, just one other thing to point out.
I'm going to give you the mic
Oh,
just
yeah.
for the recording.
So just one thing to point out, confidence interval for the minimum estimator. We probably don't want to attempt to do that because the minimum estimator is a degenerate test statistic. But one of the things that was a little bit of follow-up work to this work, which happened in 2016, which never kind of, which I was doing, but then I got pulled aside to some other projects, was figuring out the right test statistic for doing statistical analysis. So the minimum estimator is the right test statistic for solving the problem that we were talking about earlier with trying to decide basically how many repetitions of the benchmark we should run to overcome certain kinds of timer accuracy and precision error. But it is not the thing that you want to use when you're comparing two programs, essentially, and trying to figure out which one runs faster. Because of the fact that it's a degenerate test statistic. So you can essentially use like a normal test statistic, like a studentized mean or something, if you want, but then the problem becomes that you don't know the actual timing distribution for these programs. You have to learn them. So some of the follow-up work there is basically trying to use like non-IID assuming bootstrap methods, like subsampling bootstrap, to try to estimate the distribution, and then using kind of a nicer estimator that has a better ability to like actually calculate statistical significance for like a mean or something. So if anybody's interested in doing that kind of work, please come talk to me because it needs to be done. Yeah.
Thanks.
Any other questions?
I really like the argument you were making about all of these biases. Can you explain what was the solution in the end that you picked? I missed that bit for estimating performance.
Sure. So I think maybe it was unclear because we haven't fully solved the problem. We solved just one small aspect of the problem. So going back there, let's see. So the problem that we really looked at was, excuse me, it's not the right side. Yeah, I think this is our main result in the paper. So this was looking at the balance between finite timer resolution and the fact that if you just run multiple copies of the program, we think that this will get a more accurate program timing. So there's a trade-off between two different sources of error, right? One is the delays introduced by this noisy machine, and the fact that the timer itself might have finite resolution. So, for example, if you're benchmarking a really small function like x plus 1, and then your timer has a resolution of 1 microsecond. Like, so we think we have a solution to this particular problem, but as Jared was saying, we don't think the minimum is necessarily the right question of comparing the two programs. We haven't solved that problem yet.
But a lot of the benchmarks are running a bit longer. So it's the problem of benchmarking short-running programs one worth solving?
In practice, we have a lot of these in the base system, and I know Jared wants to say something.
Yeah, so I think the main point, right, is the overarching goal was figuring out how to run a large benchmark suite. At the time when we started, we had about 1,000 benchmarks. Now we have about 4,000, and that's really too many. People, I think, got excited because it was very easy now to write benchmarks. Just maybe we shouldn't have given them that capability. But the reason why it's important to be able to accurately time short-running benchmarks is because short-running benchmarks are the ones that are going to be most respectful of CI time. So if you're a developer and you want to merge a pull request and you want to run performance tests first, then you don't want to waste a lot of time running really long-running benchmarks, which might be a more accurate representation for application performance, but is not a good use of continuous integration time. And so that's also why it was important to find an algorithm that could automatically kind of, given a benchmark, tune it to figure out what the right number of times was to actually run it, because then you can minimize your kind of experimental budget time running these experiments, and that's important for CI.
It seems to me that the results that you were showing about Nano Soldier, complaining pretty much every single time, suggests that there's something wrong, right? You're getting too many false alarms or too many alarms.
Exactly. So that's because we don't have any sort of statistical significance testing, which is what I was saying earlier. Is we haven't solved that problem yet, and that's what I was saying is kind of ongoing work that I think personally can be solved if we kind of figure out the right non-IID, like assuming methods for estimating the distributions of these programs. Then we can start doing things like calculating statistical significance and using that to filter out the results. Right now it doesn't. Right, it just takes the. Right now it just takes the minimum of the 2 times. So we cache the number of repetitions we need. We tune that once offline, and then it uses those tuned numbers basically every time. Then we tune occasionally. But that way we're as respectful of experimental time as possible. But we definitely, it would be great to have a way to really quantify statistical significance, which right now we don't have a way to do so. And you can't really do it meaningfully for the minimum anyway. So we have to pick a different test statistic and then also find a way to calculate statistical significance without having IID assumptions.
Looks like we have a comment in the back.
I don't know much about this. I mean, with what you're talking about for calculating the statistical model of the times, do you think that one model could capture every one of the 4,000 benchmarks that you have? I mean, that seems to be one of the problems you have is you be building different models for different classes of benchmarks, right? That's how you do it.
I don't know, am I supposed to? Okay, anyway. Okay. Right. So it's a good point, and so that's kind of the point is you have to learn the model, right? You have to have an algorithm for learning, for trying to estimate the distribution, the actual distribution of the benchmark before you can do any kind of hypothesis testing or whatever you want to do. So I think that's right. I don't think there is technically, if you look at our statistical model, it converges to some distribution, but I don't think that distribution is useful really for the purposes of comparing two programs. It's kind of at the limit of everything, right? And I can't remember what it was. Was it a gamma distribution? I don't know.
So the gamma was a model we tried very early on, so we didn't actually publish those results. But just going back to the question of model-specific benchmarkings, I think just looking at this equation, you can kind of see that there is an issue, right? Because all of the ugliness of running on a noisy machine is in the second term here. So you have to see exactly how many delay factors were involved, how many of them each one ran, and so that's I think where the model specificity for each problem comes in. Where we think some of these things are going to be I/O heavy, they're more likely to trigger swappiness. Other things are maybe memory intensive, so they're going to hit cache invalidation or thrashing issues, things like that. Yeah, so at least at a very, very low level, just saying here's some common language and terminology we can use to talk about all the possible problems. I think this is still sound. How we actually analyze this is I think where all the details come in. So when Jared said something about the gamma distribution, so you could actually plug in here a gamma distribution for the distribution of characteristic times or the counts or things like that, and then you would be able to derive something better, but you have to assume something further on the model than just saying that there are delay instructions. We need to actually characterize it some way.
Yeah, it's like a parameterized gamma or something. Because you don't know what the parameters are.
Yeah.
So I have a question as well.
Sure.
So towards the end of the talk, you discussed nanobot, which was something that I suppose contributors can
Yes.
ask to run the benchmarks on. Did you say it was your server that was at MIT? Yeah, so the question is really, how do you make sure that each time someone asks NanoSoldier to run specific benchmarks, there's independence between those benchmarks that are being run? For example, if I am a developer, I ask NanoSoldier to run some benchmarks, then some other developer asks them, 5 or 10 seconds later, the caches are still going to be warm from the previous runs, right? So how do you try and make sure that that doesn't happen?
The short answer is we don't, and we actually try to write down a statistical model that is robust despite that.
I disagree.
Yeah, you don't think so? Okay, perfect.
We do try. So there's a couple. Since this work was a couple years ago, there's a couple details I don't really remember, but we do. So we're running on Linux, right? And there's a couple of kernel APIs for flushing the cache and doing stuff like that. And so we do those things. We run. We've done a lot of work trying to basically make the machine as quiet as possible. So there's a whole body of research on OS quiescence is what they call it, and we've implemented and compiled a lot of the techniques from that work in order to do this. I think there's still. I think Zhao's right that we don't solve this problem, right? Because the machine's still stateful. And particularly, I think there's some stuff that is happening on that machine that I still don't understand after months of trying to work on it. We do kind of attempt to clean things up. In the BenchmarkTools repository, there's actually a document that you can go and look at where we've documented a lot of the techniques we use for machine quiescence, and so some of that might be useful.
Yeah, so I think it's part of this improved reproducibility column here. So there are things that we can do at the OS level, sometimes even at the hardware level, in order to reduce the variability. But I'm not sure if we actually prevent someone from overloading NanoSoldier by asking for 1,000 benchmarks to run right away.
It has a job queue and everything.
Okay,
it waits.
yeah. Okay.
We also have multiple basically machines. It's a cluster. We have multiple actual CPUs and stuff that are very decoupled as much as possible. So we try to round robin.
Yeah. So I'm part of a team at King's College London that did the warm-up paper. I had no part of it, by the way. But they've developed a piece of software called Cron, which tries to remove OS non-determinism as much as possible. I wondered whether you'd had a look at that and looked into using that for your benchmark runners.
Was that the 2017 paper?
It was, yes.
Yeah, so I haven't, but I would like to.
Cool.
We should talk.
Yeah. Anyone else?
Well, just a quick question. And the Talus from 10 years ago from Firefox, have the statistics that they've done is of any relevance here?
I didn't hear the first part of your question.
Talus suite since 2007 that Mozilla has been using for this and statistics they are using for performance regression testing. Is
I would have to.
Comparing to that.
I would have to see. It's been a while since we wrote the paper, but I don't. That doesn't ring a bell. It might be something that we looked at.
Yeah,
I remember it.
Yeah, we could have missed it, but at the same time, I think there's, I don't think we've quite seen a paper that, at least at the microscopic level, tried to even quantify how non-Gaussian things can get. And I don't know about talents in general, but there are a lot of papers out there that just say, oh, it's sort of Gaussian, or it's almost Gaussian, you can just correct for it. That's the kind of thing we're specifically trying to avoid.
Okay, so if there's no more questions, I think we'll leave it there. Thank you again to the speaker.